So good morning and welcome back to the second session this morning. Without any further ado, let's get started with the last lecture by Nils in this series.
Okay. So as before, let's start with a quick recap of what happened yesterday. So yesterday we were trying to figure out how to characterize the gravitational waves that are being sent out by these super-dense clouds. And the approach to that problem we took was to use this so-called Newman-Penrose formalism. In which you, instead of treating the linear metric perturbations, H alpha beta, you then convert these 10 degrees of freedom into a set of Newman-Penrose scalars. And then we found that we only really need to care about one particular one, which we called psi4. And this psi4 contains the gravitational waves that we're interested in. Basically the plus and the cross polarizations. And at the same time, the gravitational wave energy flux. We also expressed in terms of this okay. So basically, this daunting task of solving, 10 second order PDEs to get the gravitational waves reduced to just finding this Newman-Penrose scalar at very large distances. And so that would automatically give us the plus and cross polarizations and obviously also the gravitational wave energy flux. Okay, so how do we do this? Basically, we followed Tucholsky's approach. Who analyzed exactly this problem in that, trying to understand linear metric perturbations on a Kerr spacetime. And we were able to, or Tucholsky was able to reduce this problem to a set of 2 second order ODEs. So that was a polar equation as well as a radial equation. And so the solution for the polar equation, we kind of assumed we knew, which we then called the spin-weighted spheroidal harmonics, similar to the spherical harmonics, just slightly different, basically. And so then the task of finding psi4 reduced to solving the sourced radial ODE, where we used a Green's function approach. To basically reduce solving this to basically a single integral, okay? So the solution to the radial equation at large distances, which is all we're interested in, we found to be some particular expression that I'm just gonna copy now. That crucially is an integral from the horizon to infinity of some homogeneous solution to the Tucholsky, the radial Tucholsky equation, which we know people have found before, multiplied by G, which is basically the source, so the right-hand side of the radial equation, which is some function of our super-aliens cloud, and then just weighted by some function of R plus. Okay? And so this R then enters in our psi4 in a particular way. And so ultimately, all we need to do, or quote unquote, all we need to do is perform an integral over functions that we know. Okay? Okay. And then I basically gave you the solution of what comes out, at least for the gravitational wave energy flux. And the solution looks, roughly speaking, like this. So you have some constant C, and then you have, for a small alpha, this solution looks something like this. You have some scaling, some power P in alpha, and then this gets multiplied by the cloud mass over the black hole mass squared. And so this is just some number. Okay? And so this number will be different for the scalar and the vector gravitational radiation. So the gravitational radiation from a scalar cloud or a vector cloud. This power will also be different, and it will also depend on the particular state you're looking at. So for instance, in m=1 state, we will have a different power than m=2 state. And similarly, the vector clouds will have different numbers. And then this is the same in all cases. Okay. Then we also learned that the frequency of the gravitational wave, so the angular frequency omega GW, is exactly 2 times the angular frequency of the superhélice cloud. We learned that the azimuthal number of the gravitational waves is also exactly 2 times the azimuthal index of the superhélice cloud. And that's where we left off. So I just want to briefly complete the discussion of the gravitational waves and then move on to how we can use all this machinery that we have been writing down for the last 4 days to actually look for these new particles and motivate why these new particles, or why some people believe these new particles should actually exist. Okay, so basically the most unstable state, so basically the superhélice state that grows the fastest, we found to be the m=L=1 for scalar fields. Okay, so this implies that mGW for this state is exactly 2. Okay, and then it turns out that at least for alpha much smaller than 1, going through the calculation of actually doing this integral, plugging this into psi4, and then extracting the plus and the cross polarizations, you find that the LGW mode, the gravitational wave mode, the polar gravitational wave mode is also exactly 2. Okay, so basically what this 2,2 means is that it's just kind of the most important contribution to the gravitational waves is in the quadrupole emission. Okay, and so to just briefly write this down, I'm going to define some characteristic strain amplitude, which is basically just determined by the total gravitational wave energy flux, the frequency, and then dl, d sub l denotes the luminosity distance, so just the distance from us to the source. Okay, and then the plus polarization for this 2,2 is basically just h0/2, 1 plus cos squared theta. And similarly, okay, just to give you a flavor of, you know, what the dependencies on the polar angle, time, and phi are. Okay. Okay. And so then the question is, okay, we started out with basically no supervariance cloud. This cloud then grew exponentially quickly, saturated at some finite value where it contains some fraction of the black hole's mass. And then it starts radiating, mostly in the quadrupolar gravitational waves. But of course, the energy that's contained in the cloud needs to dissipate over time because we're radiating the energy away through gravitational waves. Okay? So how can we understand exactly the time dependence of the mass contained in the cloud once this gravitational wave emission becomes efficient? And basically, this is something that you already did yesterday in the tutorial, so I'm kind of repeating what you already derived, but just so we're all on the same page. The basic idea is that we know the energy flux of gravitational waves that are being sent out by the cloud. And so we can write down, let's call this cloud evolution. So we can write down a simple evolution equation for the mass of the cloud in terms of the gravitational wave energy flux. And so there the assumption is simply that the change in mass of the supervariance cloud is purely due to the emission of gravitational waves to infinity. Okay, this is basically just energy balance that, okay, there is some finite mass in the cloud and everything gets emitted into gravitational waves. Okay? And so this is basically, some function of alpha, some function of spin, but then cloud mass over black hole mass squared. Okay? And so basically, this is just an ODE, right? So you have, MC dot over here, then you have an MC squared over here. So it's just a matter of solving that ODE. And the solution to that ODE is the following. It's generally of this form, where MC sat is basically the mass of the cloud at t equals 0, where I define t equals 0 to correspond to the saturation. So saturation at t equals 0. Okay? So t equals 0, it just contains basically the complete mass of the cloud, so what we learned, up to 10% of the mass of the black hole. And then over time, of course, it kind of decreases, roughly speaking, polynomially in time. Okay? So eventually, at t to infinity, this is just 0, and there's no energy contained in the cloud at all anymore. So what is this tau GW? Basically, the tau GW is just some time scale over which this happens. And this time scale is, you can get that directly by just imposing that at t equals 0, the cloud mass should be the saturation mass. This time scale is this, okay? So how to understand this time scale? Basically, the cloud mass at the time of one time scale, okay, is equal to just plugging this into this down here, is basically equal to the saturation mass divided by 2. Okay? So after 1 tau GW, the mass contained in the cloud is exactly 1/2 of what it was originally. Okay, so it just gives you like a rough idea of what the timescales are for the decay of the supervariance cloud due to gravitational waves. Okay, and then of course you can just get the tau GW by plugging in the expressions for the gravitational wave energy flux that we wrote down yesterday, and can actually get some feeling for what these numbers are. And I'll write down some numbers in a second, but interestingly, what you'll find is that the tau GW is typically, for the most part, much larger than the e-folding timescale of the superradiance growth. Okay, this is just something that pops out of the math. And what this means is that basically you can split the evolution of this black hole cloud system into two phases, right? The first phase, where the mass of the cloud grows exponentially. That's the superradiance phase. And so if you start at some time, it will just grow exponentially. Okay? But then, of course, at some point, it reaches a saturation. So this is kind of the saturated cloud mass, or the log thereof. And so all of this regime, we're going to call the superradiant regime. Superradiant. Okay? So here, basically, the emission to gravitational waves doesn't matter at all, because the timescales of the emission are so much longer than the growth timescale. Okay? But then, of course, over time, as we just found out, the growth stopped, right? So the timescale of the growth goes basically to infinity. Okay? But then the cloud still decays over time, roughly polynomially. So in this plot, it will look something like this. Okay? And so this is the gravitational wave emission timescale. Emission phase. Okay. And so the clear separation of scales you can see in this plot basically by noting that the growth happens extremely quickly, and then the decay just takes a very, very long time. Okay. And then the last thing I wanted to mention, and this will be important for actually searching for the gravitational waves that are being emitted by these superradiance clouds, and that is the frequency evolution. So we found that the gravitational wave frequency is basically just 2 times the cloud's frequency. Okay? But the cloud's frequency doesn't change really over time. Okay, so basically what this means is that the gravitational wave frequency is just fixed at one value, which basically just means you have one wave that has a roughly constant amplitude, but a single frequency, which is a continuous gravitational wave. Okay? And to look for these continuous gravitational waves, you kind of need to assume exactly that you have some fixed amplitude, you have some fixed frequency. And so as soon as this frequency, or as soon as this assumption is no longer the case, then the search methods that you use to search for these gravitational waves might not apply anymore. And so one important way in which it can evolve over time is that the frequency is actually not exactly constant, but it changes in time. Okay? And so let me describe exactly why it changes in time, and then give you a formula for the amount it changes in time. Okay, so to physically understand why it changes in time, let's recall gravitational redshift. Okay, so basically, in a Schwarzschild spacetime, so I'm focusing on Schwarzschild here just as an example, because I imagine you have seen that calculation at some point. But of course, the same is true for Kerr or for any massive object. Okay, so the frequency of let's say a photon that you detect at infinity is equal to the frequency of that photon sent out at some radius r, multiplied by this factor. Okay? So basically what this means is that the frequency at infinity is more than the frequency that the photon had when it was sent out. Okay? Okay. And now imagine that, okay, these gravitational waves are of course not, photons, but imagine you have a single graviton that is being sent out from some quote-unquote location in the cloud, and then it has to climb out of the potential well to reach infinity. Okay? So basically, you had some frequency at the location, quote-unquote location, where it was sent out, and then it reaches infinity and it has a slightly different frequency. Okay. Now, this doesn't really matter because we only detect the gravitational waves at infinity. So what the gravitational waves went through on the way to us doesn't really matter, right? But what does matter is this m here, right? Because we know that the mass of the system changes over time, right? The cloud mass, or the cloud extracts some energy from the black hole, and then the mass decays over time, okay? So at late times, we're basically left with no cloud, but a black hole that has a lower mass, okay? And so what this means in this formula is basically that the mass at the beginning is slightly larger than the mass at the end, okay? Which also then means that the frequency of the gravitational waves at the beginning is slightly lower than the frequency of the gravitational waves at late times. Which basically means that the frequency has to wander from like a small value or a small-ish value to a slightly larger value over time. Okay? To make this a bit more concrete, so we start out with some system mass ms for m start, which is larger than the system mass at the end, me, which then implies that this frequency at the start, which is this formula, is smaller than the frequency with the mass me, which is equal to the frequency me at infinity. Okay? So the frequency at the end is larger than the frequency at the beginning, which basically means that you have a spin up or an increase in frequency. Okay? Okay, and you can basically treat this in, you can try and derive a formula for this using Newtonian methods. Basically, you compute the Newtonian potential of the superradiance cloud in the beginning and at the end, and from that you can compute basically what this end value is and what this beginning value is and what all the values in between. Okay. But generally speaking, this hasn't really been worked out fully yet. Okay? So we only really know a rough estimate for alpha much more than 1. And so there, and now I'm just going to give you the expressions basically. In the case of the vector, the gravitational wave frequency shift is the following. and this is for an m equals 1 state. Okay. Okay, so basically now we have more or less learned everything there is to know about superradiance clouds, or at least superradiance scalar clouds, and the way we get gravitational waves from these superradiance clouds, and what the properties are of the gravitational waves. Okay? And so the properties basically are, it's a continuous wave with some set frequency, and the frequency evolves ever so slightly in time. And the amplitude of the gravitational waves is basically the square root of the gravitational wave energy flux, and therefore it's proportional to the mass of the superradiance cloud, and therefore it decays slowly in time. Okay? But basically it's a continuous wave with a set amplitude. Okay, so just to give you a flavor, and some of this you already did during the tutorials, but just to give you a flavor for all these numbers, not just in terms of g equals c equals 1, but in actual like human readable units. So let me start numbers. So let me start with alpha, okay? So alpha is basically the mass of the boson times the mass of the black hole. And so plugging in some normal numbers, we get something like this. Okay? So what do we learn from this? What do we learn from this? Basically, what we learn from this is that we know that the superradiance process is most efficient if alpha is roughly order, let's say, 0.1, okay? 0.1 or 1, okay? And so basically, we want this alpha to be exactly in this regime. And to achieve that, we need to basically tune those two numbers such that that's the case, okay? Now, of course, we know that we only have black holes of certain masses in the universe, right? We assume the lowest mass black hole is something like a couple solar masses, let's say, and then the largest mass black hole is, let's say, 10 to the 9, 10 to the 10 solar masses. Okay, so that basically tells us a regime for this number. And then conversely, for each black hole, we can then work out what the boson mass should be, such that this is the case. Okay? And so to do that, let's assume that we have a solar mass black hole. So here I'm going to assume the black hole mass sits somewhere in this regime. And this corresponds to a boson mass of somewhere between 10 to the minus 11 electron volts and 10 to the minus 14 electron volts. Of course, this is only roughly true because we don't need alpha to be exactly one number. It can be a range of numbers, right? So this is only a rough estimate, but yes. So basically, around solar mass black holes, the superradiance process, so the production of the superradiance cloud as well as the subsequent gravitational wave emission is most efficient if the boson mass is in this ultralight mass range, so from 10 to the minus 11 to 10 to the minus 14 eV. Okay? And then similarly for supermassive black holes, which I'm going to assume to be 10 to the 10 solar masses to 10 to the 5, we get boson mass of between 10 to the minus 15 eV and 10 to the minus 20 eV. Okay. So basically the black hole population that we believe exists in the universe dictates which boson masses we will be able to probe through the superradiance mechanism. Okay. Okay, so before going to explain exactly how we can use continuous waves and other methods to look for gravitational waves and therefore infer the existence of these ultralight bosons, let me quickly recap the whole story so everyone is on the same page. Okay, so we started out with some black hole of some initial mass and some initial spin. Okay, this we just assumed existed in the universe somewhere. Either we have observed it through X-ray observations, or we have observed it through gravitational wave observations, but somehow we know there is a black hole there. Okay. Then we assume that, okay, this black hole has a particular mass, so maybe it's a solar mass black hole. And then if there is a particle of this particular mass that exists in the universe, then this particle must trigger the superradiance instability, right? So the tiniest perturbation of the presence of this particle will trigger this instability, okay? So over time, we're then growing this superradiant state around the black hole. Okay. And basically the dynamics here is exponential. This happens exponentially quickly over some time scale or some growth rate, omega I, proportional to C. Okay. And then the frequency of this superradiant state is basically approximately equal to mu, where mu is just the mass of this boson. Okay. Then we also found out that, okay, this superradiant state now no longer has the initial mass, the black hole inside the superradiant state no longer has the initial mass and the initial spin, but now has the final mass, which is smaller than the initial mass, which is initial mass minus this expression, right? And similarly for the final angular momentum. At this stage, where it's saturated, we found that the saturation condition is precisely setting the frequency of the superradiant state to be m times the horizon frequency. Okay, so at that point, this exponential growth shuts off, and there's some finite mass contained in this cloud. And we found this mass to be up to 10% of the black hole's mass. Okay? And then we just found out today that basically the final state of the system is one where the cloud is very small. Okay. And it got there through gravitational wave emission. Okay, so this is the gravitational wave emission. Okay. And in contrast to the initial phase, the superradiance instability, this happens over polynomially long timescales. Polynomial. Okay, so it's a much, much longer process than the exponential growth originally. So here the relevant timescale we found to be the gravitational wave timescale, tau GW, which, if you plug in some of the numbers, is basically, okay, so this is for m equals 1 scalar. Okay. So the emission timescale is basically, very, very long for small alpha, and then decreases as alpha becomes larger. Similarly, we found the frequency of the gravitational waves to be basically just 2 times the angular frequency of, or 2 times the frequency of the oscillation of the cloud. And so that's basically omega r over pi. So what I did here is just converting the angular frequency to the real frequency. Hence the pi, and the 2 disappeared. Okay. And then lastly, what we just found out is that the gravitational waves, the frequency of the gravitational waves isn't actually constant and fixed at some particular value, but there is some slight drift in time. And this drift we found to be, or I wrote down to be, the expression over there, but crucially non-zero. Okay? But then also the question is, what happens afterwards? Okay? So we had some state, so let's assume we had the m equals 1 state of a scalar field grow around this black hole. It grows exponentially over some time. Great, we're forming the superradiance cloud. Okay? The superradiance cloud over a very long time scale decays to gravitational waves. But then what happens afterwards? Well, actually, this black hole that we're now left with here, even though it has lower mass and lower spin, is still unstable to the superradiance instability. Just not the superradiance instability of the m equals 1 mode, but now the superradiance instability of the m equals 2 mode. Okay? So basically, then this process repeats. It grows exponentially yet again. We produce another cloud. This cloud decays through gravitational waves. And then we were left here again. Okay? And then it will, in principle, decay to m equals 3, and so on and so forth. Okay? Now, I should mention that, of course, the larger the azimuthal number, the longer all of the timescales. Okay? So for the m equals 1, the timescales are the fastest. The exponential growth happens the quickest, and then also the decay is the quickest. And for the m equals 2, this is already orders of magnitude smaller. The timescales are much, much longer. And so this process just takes longer to complete. And so typically speaking, we're not interested in these higher order modes because we know, roughly speaking, how old black holes should be. And then just looking at the numbers, usually we're only interested in the m equals 1 because it just takes so long to grow any of the higher order modes. But in principle, this would just go on forever. Right? Right, so the black hole doesn't evaporate because there's this irreducible mass in there which you can't touch at all. So that will always either be zero, will not change, or will increase in time, right? So that's always there, so the black hole will always remain there. However, the spin can reduce to 0, right? And so that is exactly what happens. You spin down the black hole, but because the final spin here is larger than 0, of course, so, okay, maybe I should write down the expression so we can talk about it. What is the expression? So the final spin of the black hole in the small alpha regime becomes very, very small, but it's non-zero, right? Because for alpha equal to 0, the system is not unstable, right? But that means that it is strictly larger than 0. And so that means you always still have some amount of angular momentum left. The amount can be minuscule, but in principle, this process will still go on. But of course, the cloud mass can no longer be 10%. It will be smaller and smaller every single time. Okay. Okay. Okay, so now let's move to some amount of particle physics. Because I think it's important to not just go through this calculation and then just assume at the very end of the day that, oh yeah, there will be some particle that we believe to be there in this mass range, right? We need to first understand, okay, do we actually believe that this particle exists seriously, or are we just making something up, okay? And so basically, I just want to give you a couple of ways through which people motivate these particles and discuss their existence. But I won't have the time to go into all the details. So if you have any questions about it, just come up to me afterwards. Okay, so the first one is usually called the strong C-pre problem. So basically, the quote-unquote problem here is that, okay, first I should say strong refers to QCD, okay, so quantum chromodynamics. And CP stands for charge parity. Okay, so basically, we believe, or there is no reason to believe that a term of the following form is not contained in the QCD Lagrangian. QCD. Let's put a question mark here. Okay. So if you have never seen, who has seen a QCD Lagrangian? Okay, some people. Okay, if you have never seen the QCD Lagrangian, it doesn't really matter. Okay, just picture this G to be the field strength tensor from regular E and M. Okay. it's obviously slightly different, but that's kind of the picture. And this star here denotes basically what's called the dual. So basically what this means is that instead of in E and M, so let's write E and M, the Lagrangian is something like -1/4 f mu nu, right? Instead of the f, you then have an f star here, which is basically a dual which breaks the parity. So basically, this is no longer parity invariant if you flip the spatial coordinates, basically. And so what this implies, not in the case of the E and M, but in case of QCD, what this implies is that, for instance, the neutron, which is made up of quarks, which are described by QCD, develops an electric dipole. Let's call it D. Okay? So if this term is present in the Lagrangian of QCD, and therefore in the standard model, then any neutron should have some electric dipole moment. Okay? But the thing is, we can measure this electric dipole moment, and we know that this is very, very small. So currently, there exists some upper bound, but of course, we don't know the value. We just know that it is smaller than some upper bound. Okay? And because this is so small, this also implies that this coupling constant gamma must be very small. Okay? But that's odd, right? Because a priori, this would be kind of a fine-tuning problem. We're saying, okay, this term should be present, but really the coupling should be very, very close to 0. And so we're fine-tuning it to be very close to 0 as opposed to some other number, 1, 2, 15, you know? And so this always makes particle physicists nervous if you do some kind of fine-tuning to match two observations. And so the way to get around this is to introduce a new particle. So you introduce the axion. This was done by Pecky and Quinn back in the, did I write it down? 60s, 70s maybe. And so the idea is that instead of having gamma here, you replace the gamma, the coupling constant, by a new scalar field theta. Okay? And this new scalar field theta has a potential such that when theta equal to 0, the potential is 0 or minimal. Okay? And so that just tells you that dynamically, this new scalar field phi wants to go to the minimum of the potential, and the minimum of the potential corresponds to gamma effectively being 0. Okay? So this is a dynamical way of solving the strong CP problem, which is this fine-tuning problem that this term shouldn't be present in the QCD Lagrangian. Okay? But what this implied is that we now have a new particle called the axion. And this new particle is a scalar particle. And in some cases, it can be ultralight, and therefore 4 in the mass range that I wrote down over there. Okay? So this way is one way to motivate the existence of at least one scalar particle. Okay? Then the next one is kind of the more or less most obvious one, that's dark matter. So we think that dark matter is some new particle that we haven't discovered yet, but we don't know what it is. And so people have come up with different theories around this, and one potential candidate is fuzzy dark matter. Or ultralight fuzzy dark matter. And basically what this is just a scalar field that has a mass that is very small. So something like, I don't know, 10 to the minus 16 electron volts. Very, very small, okay? And so people believe that the dark matter is at least, or it may be to some extent, made up of this of this ultralight scalar particle. And then lastly, there are also high energy motivations. So basically one of those would be string theory. So I guess I'm not sure how familiar you are with string theory. Has anyone taken a string theory class? Okay, one. Okay, well, basically the idea is that you need this, you might know. So you need these many dimensions, right? 10 or more. But of course, we're living in a four-dimensional space-time. And so somehow you need to get rid of these dimensions, and that's typically done by compactifying dimensions in specific ways. And this compactification process introduces additional particles. And these particles then may be of the relevant mass that we are interested in, okay? So new particles. Okay, so we have three, debatably compelling ways of motivating the existence of ultralight particles. And so, okay, we somehow have a theoretical preference for the existence of these particles. So let's try and search for them, or at the very least, put constraints on their existence. Okay. Search strategies. Okay. So how could we possibly look for signatures of this superinfluence process? And then, in turn, infer the existence of the superinfluence cloud, which in turn can only exist if we have a new particle of a particular mass. Okay? So ultimately, we're interested in signatures of the presence of the cloud, which then implies the existence of the particle. Okay? So it's kind of an indirect search for these ultralight particles. Okay. And so the first and perhaps most obvious way of searching for this is doing a spin measurement. Okay. So why is that kind of the obvious way? Well, because during the superinfluence process, we're extracting a lot of angular momentum from the black hole. And we know that, at least in the small alpha regime, the final spin must be vanishingly small. Okay? And so basically, we have this weird and very efficient, because exponential, process to reduce black hole spins. Okay? And so if we looked at a population of black holes, and we mapped out all of their masses and all of their spins, then we would expect there to be kind of a hole in the plot where the superradiance particle, where the ultralight particle induced the superradiance and reduced the spin of all of those black holes. Okay? So basically what we would be looking at is the following plot. We have the chi, so the dimensional spin of the black holes. You have the mass, okay? And then we do a bunch of measurements of a bunch of black holes. And they all have different masses and different spins. Okay? But at some mass range, there happens to be no black hole in some mass and some spin regime. Okay? And so basically what we can do is we can, based on this plot and based on measuring all of these spins and masses, we can then say, okay, in this regime, maybe there's a superinfluence process active that have reduced the spin and and mass, but mostly the spin, of all of these black holes down to some smaller value, okay? And kind of the smoking gun here is that, okay, you started out with some, let's say, uniform distribution of black holes that has, spins from 0 to 1 and in some mass distribution. And then the superhens process kicks in around all of these black holes that satisfy the superhens condition. And all of their spins get reduced, okay? So they kind of start out up here, but then they lose their spin, and so they move in this plot down here, okay? So what you expect to happen is that you have this accumulation of black holes at the lower line here, where basically the, in this case, the m equals 1 mode saturates, okay? And so basically the two things combined, you look at the population, you see some sort of hole in this plot, and then secondly, you see a bunch of black holes kind of lined up at the bottom of this line, will be a smoking gun signature of the presence of a particle that must have driven the superhens process that extracted all of the angular momentum that led the black holes to sit down. Okay? Now, how can we do a spin measurement? Okay? So masses are a bit easier to measure because we have orbiting things. We can measure the period of orbiting things, which then implies the mass of the black hole. But the spin is a little more complicated to measure. And so, well, we kind of know of two different ways. So there's the way to use electromagnetic emissions. These are, let's say you're looking at a low mass X-ray binary where the companion is some star that feeds an accretion disk around the black hole. And then you can see this accretion disk through, let's say, X-ray or some optical observations. And then based on some properties of the X-ray or of the electromagnetic emissions, specifically absorption lines, or emission lines, in the spectra from these systems, you can then, assuming some disk model, infer the spin. Now, this is typically considered to be challenging. And the reason it's challenging is because ultimately the only observation you have of this black hole is you have a spectrum, right? You can't resolve the actual spatial extent of the accretion disk and much less the spatial extent of the black hole itself, okay? So basically you need to model all of the accretion flow that goes on around this black hole in such a way that you believe you understand the accretion flow sufficiently that you can then use the spectra you can measure to infer a value for the spin, okay? And that step, so basically this error here, typically is considered to have a lot of systematic uncertainties because you don't know what the accretion flow actually is because there's no way of measuring the accretion flow in any particular way, okay? So here we have typically large systematics. Okay. But then, of course, we know of a second way of measuring the spin, and that's using gravitational waves, okay? Because if we have a binary black hole that spirals in, then we can measure the spin, not just of the remnant black hole, but also of the in-spiraling black holes, okay? And we assume that the in-spiraling black holes were coming from a black hole distribution that looks something like this, okay? If we have an ensemble of black holes, some of them will merge over some time, and these binaries are made up of black holes from this population, which has a hole somewhere, okay? And so basically what we're interested in is not so much the spin of the remnant, but instead the spin of the constituents of the binary before they merged, okay? But the disadvantage using gravitational waves is that at least right now, the sensitivity is not good enough to actually constrain the spins of the initial binaries, okay? So not well constrained. So there have been some studies that basically did this, that tried to fold in this information, and then from basically the distribution or the posteriors of the spin measurements that we have, basically the error bars on the spin measurements, then translate that into basically reproducing something like this, and therefore inferring that, okay, what they observed was that the spins were not unusually low, which basically implies that there shouldn't be a superradiance cloud around any of these black holes, which then in turn implies that no boson of some particular mass range should exist. Okay? So people have done this, but typically these constraints aren't very confident because the data is just not good enough yet. Okay? So the bottom line of these spin measurements is that, yes, they're very effective if we could actually measure the spin very well. Okay? But we just simply, at the moment, aren't able to do this very accurately. Okay. So now, let's move to continuous gravitational waves. So now, instead of looking at the black hole that is left after the superradiance process went through, we're now hoping to actually catch the superradiance cloud itself. We're trying to catch the gravitational waves sent out by a superradiance cloud around some astrophysical black hole that currently exists, right? So we could be in a regime where this just takes so long that the cloud hasn't formed yet, or we could be at a time where the cloud has already decayed and is very small. Okay? So we have to be a bit careful in interpreting exactly what we mean, but now we're going to assume that we are in a state, or at a time, where the particular black hole that we're looking at has a superradiance cloud that emits continuous gravitational waves. Okay? So then the question is, how can we look for these? And so I'm not going to describe exactly how to search for continuous gravitational waves, but I'm going to describe the strategies we can use the continuous wave methods to then constrain these ultralight bosons. Okay? So perhaps the easiest one, quote unquote easiest one, is a so-called all-sky search. So basically what is done there is that you're looking for continuous gravitational waves, and you're completely agnostic from where they might be coming from, okay? So you're just looking for basically coherent continuous waves power in all of your detectors. You have no idea where they came from, okay? So this is great because we have no idea where the black holes are, right? We kind of know, okay, we have some black holes in the Milky Way, so maybe they're, kind of in the galactic plane. But apart from that, we don't really know where they are exactly because it's very hard to find out where black holes are, right? And so in that sense, these all-sky searches is great because we would just be capturing any black hole that has a superradiance cloud around it and sends out gravitation. The downside, of course, is that this is basically reducing the sensitivity of what you could be doing with the continuous wave search to kind of the lowest possible. Because if you know where the continuous waves are coming from, you can do a much deeper search for continuous waves from that point in the sky. Okay? So that is just a problem of the sensitivity of the search. The second problem is, so let me say, not very sensitive. The second problem is, here, if we did an all-sky search, and then we put some upper bound on the continuous wave amplitude at a given frequency, then the question is, okay, how can we translate this measurement into a constraint on an ultralight boson? Okay? And there, of course, we need to make a bunch of assumptions. because as I said, we don't know where the black holes are. We don't know what the black hole mass is. We don't know what the black hole spin is. We don't know what the black hole distribution is, what the total mass is, nothing, right? So we need to assume all of these things. We need to say, okay, we believe there is a large population of black holes at, around Sagittarius A star, the center of the Milky Way. And so if that population existed, and if the spin of this population were large, and if the masses were like this, so we need to make a bunch of assumptions. And if we make those assumptions, then we can translate the upper bounds obtained from the all-sky search into constraints on both ultralight scalar particles and vector particles. But of course, as you can tell, there are a lot of assumptions. Okay. So basically, that's not the optimal way to do this. Then we have targeted searches. Okay, so as I was already mentioning, if we know where to look, we can do much better. Okay, we can't just do much better in terms of sensitivity, we can also do much better in terms of knowledge of what we're looking at, right? Because we know from certain EM observations that, we know low mass X-ray binaries exist. Some of these are black holes, and we have at least some measurement of the mass. Okay, of course we could believe the EM observations as well for the spin, but even if we're agnostic about the spin, at least we have some amount of information around about the source that we expect to be there at this particular point in the sky. Okay. So number one is we can do a targeted search which basically points exactly at that point in the sky, and therefore it's better sensitivity. Okay, so better sensitivity. So we're more sensitive, but we also need to, accurately know where this black hole is. And then secondly, of course, we don't need to make any big assumptions about the black hole population, because now we're just looking at an individual black hole. And we know, or we have some rough estimate for the masses and perhaps even the spin. Okay, so it's less assumptions. But by less assumptions, I really just mean less assumptions, not zero assumptions, right? Because the assumption is still that we're exactly in this particular state, right? We not happen to look at the black hole when it hasn't grown yet, the superheavens cloud, or we not happen to look at the black hole when it already decayed over time. Okay, so we kind of need to assume that we happen to be lucky that the black hole is exactly in the state where it emits gravitational waves that we can actually detect. Okay? Okay, and so there's one way to get around all of this. And that's the last search strategy, and that's follow-up searches. So here the idea is kind of similar to a targeted search, but slightly different. So here the idea is that we measure binary black hole mergers, and we then know that, okay, the remnant of the binary black hole merger is another black hole. And it's not just any black hole. We have a precise or roughly precise measurement of the mass and the spin of this black hole. Not just the mass and the spin, but also the sky location. Okay? So we now know that a new black hole was formed of a particular mass and a particular spin at a particular point in the sky. So all of these things are measured purely by the gravitational wave observation of the compact binary merger. Okay? So gravitational wave measurement of mass and spin of binary black hole merger remnant. Okay? So this basically drops all of the assumptions. We now know exactly what the mass is, we know exactly what the spin is, we know exactly the sky location, and we also know that the black hole is not in this state, not in this state. We know it's exactly in this state because it was just formed. Okay, so it couldn't have gone through this process just after. Right? And basically, because this growth timescale is much, much larger than the merger timescale of the binary, this will only happen, order days or months after the merger. Okay? So not only are we dropping the assumptions that went into the all-sky search, we're also dropping the assumption that went into the targeted search, pointing at known black holes, or known and old black holes. Okay? And so then the name of the game is basically to search for continuous waves from these remnants. And of course, since we know the mass of the black hole, and we then assume a boson mass, we know exactly how long it will take for the superhelium cloud to grow. So we can basically predict exactly this number. And so we can say, okay, we have this merger, and then let's say 10 days later, we need to look at that point in the sky. And then over some gravitational wave timescale, which could be, let's say order months, we then need to look at the gravitational waves from that point in the sky. And then after, let's say 1 tau GW or 2, when the amplitude decayed to a smaller value, we can then stop looking. And if we didn't see anything, then we can confidently infer that the superhelium cloud didn't exist. It didn't send out gravitational waves. And therefore, also the ultralight particle didn't exist. And that way, we can confidently constrain the existence of the particles without making a whole lot of assumptions. Right. So that is a good point. Yes, that could be. So it could be that one of the constituents of the binary that merges already had a superhelium cloud. But typically what happens, and people have looked at this in the last couple of years, is that when you have a binary, you then have a perturber that perturbs the superhelium cloud. And what will happen is that long before merger, this superhelium cloud will have either accreted onto the black hole or be emitted to infinity. So the bottom line is the presence of the binary, at least at the mass ratios that are relevant for ground-based detectors, so like roughly mass ratio 1, the cloud won't be present at merger. And so this exponential growth is basically from 0. Right. In MRIs, it's a slightly different story. It still depends on mass ratio. But in MRIs, what the idea is that you have this massive black hole that has the superhelium cloud, and then you have this small black hole that orbits. And basically, the idea is with LISA, for instance, you want to look at the gravitational waves from that binary. And the presence of the cloud will induce a phase shift on the binary compared to the vacuum case. And then the hope of people is that this phase shift is detectable. And then if there is no phase shift, so the absence of the phase shift would then imply that no particle can exist. Now, again, there are a bunch of assumptions that go in because, again, you must assume that this cloud existed right now while you're observing it, which you don't know because supermassive black holes have existed for a very long time. And so there are some assumptions that go into that, but in principle, yes. Yes. Okay. Okay. So the bottom line is there are various ways of doing this. We can do spin measurements. We can do all-sky searches, targeted searches. But ultimately, the follow-up search is kind of the preferred way of doing this. But in some sense, it's also the most difficult way of doing this. Okay, because yeah, basically it becomes a bit more technical now why this is so challenging. But all-sky searches are much easier to do compared to these. Let me just leave it at that. Okay. And so now in the last, let's say, 10 minutes, let me say 1 or 2 words about what people are doing at the moment in terms of research. So all of this, what I described so far, is kind of common lore. The super-N story has been worked out by many, many people over many, many years. But this process is pretty well understood. There's some kinks here, some bits there that haven't been worked out, but overall, this is pretty well understood. Then the actual searches are kind of just limited by the fact that we're not super sensitive at the moment. And so we're hoping with gravitational wave detectors improving, these searches will also improve over time, just naturally because the sensitivity becomes better and the search techniques become better. Okay? So that's, of course, one big area of where things can be improved. But then on the theory side, what people have been thinking about is basically to understand how some of these motivations here can actually lead to a change of this super-alien story that I've been telling you over the last couple of days. Okay, so let's call it current research. So this broadly classifies into a couple of main areas people are focusing on. These are, let's call it, additional couplings. Okay? So the first one people were looking at was self-interactions. So what I mean by self-interactions is that, in the Lagrangian for the Klein-Gordon field, so this was something like you then add some higher order term in the Lagrangian. And so this is then called the self-interaction. And the reason you want to do this is because of this axion motivation, or that's one way of motivating this. Basically, if you work out how this exactly emerges and how this mechanism works, then you'll find that the axion has some non-trivial self-interactions. And these self-interactions are basically just because this potential here is not just a mass term, but it's something more complicated. Okay? And so then the self-interactions may spoil this whole story because they might impact the evolution of the super-N cloud in some particular way that we don't know. And then people work this out, and basically what they find is that, yes, it can affect the super-N's growth and also the subsequent gravitational wave emission. So basically one important outcome here is that the saturation can happen earlier. So saturation happens before okay? So instead of sending out a bunch of gravitational waves, these self-interactions lead to the fact that you're sending out scalar waves as opposed to gravitational waves, okay? And these scalar waves are basically just a bunch of axions you emit from the system. But the problem is we're not very good at detecting axions because if we had detected axions, we wouldn't be doing any of this, right? So there's no way we can actually detect these scalar waves that are being emitted, and therefore we have to be very careful to place constraints if we don't see anything, Okay? Because if the self-interactions are too large, then we might not see anything even though the superheads cloud was there and even though this particle exists. Okay? So it's valuable to understand these additional couplings and self-interactions because they directly impact our constraining power. And so then additional couplings can also be not just basically self-coupling, self-interactions, but also coupling to the standard model. Okay? And there you kind of open up the can of worms. You can have a million different ways of coupling these particles in principle to the standard model. But astrophysically relevant are only a few. Okay, so for instance, just to drop some names, there's the axion photon coupling. Okay, so basically it's a particular way how you can convert axions into photons. And so you can imagine that depending on the context, this might lead to problems, right? Because now you have a very high density of axions, but if the axion can decay to photons, then you might suspect that, oh, maybe it doesn't grow all the way up and it doesn't emit all the gravitational waves, and then something similar happens that it kind of quote-unquote saturates before the gravitational waves are being emitted or before the spin is reduced, okay? So people are trying to understand exactly how this works. And equivalently for the vector, people are considering the kinetic mixing. It's basically the same as the axion photon coupling, just simply that you there convert the ultralight vector boson into a photon, okay? And then there's a bunch of new dynamics that happens there, and that might again affect the whole story and therefore your constraining power. Okay, and then perhaps lastly, what people have been thinking about more recently is spin 2 or massive spin 2 fields. So what are spin 2 fields? A massless spin 2 field is just the metric. Okay, so it's basically, imagine a spin 0 field is a scalar, spin 1 is a vector, 1 index, spin 2 is a tensor, 2 indices, and so on and so forth. And so a massless spin 2 is just the metric. But now we add a mass term in a particular way. And so basically, I didn't talk about this at all, but basically superhand instability is still present. But because spin 2 fields and coupling those to gravity is somewhat murky and complicated, there are more things happening there. So people are trying to understand, okay, can we also constrain spin 2 fields using the superhands process or not? No. Well, no. So the subgravitational theorem, and I'm not a particle physicist, but I think it's just a particular theorem on the amplitudes that you get from gravitons, and some massive lines connecting them. But you don't need to impose that some massive spin 2 field exists. You can have the graviton coupled to a massive spin 0, and I'm sure then there's a soft graviton theorem for them, for those amplitudes. Okay. And then very briefly, the second major thing that people are thinking about these days in the context of this is preparations for LISA. Okay? So LISA, if you don't know, is the gravitational wave detector that people are currently building or currently working on to then build. That's supposed to launch in 10 years, maybe a bit more from now, and sit in space and detect gravitational waves of frequency much, much lower, like 4 or 5 orders of magnitude below ground-based detectors. And so then the question is exactly what you asked. Can we observe or find some hint for the presence of supermassive clouds around supermassive black holes? And can we do so with MREs? Okay, so basically here, trying to understand the impact of the cloud on MREs. Okay, And so basically, once you put this into a binary, a lot of things happen. Because now we have a parameter space that is much, much larger. You don't just have, basically the parameters we needed was the black hole mass and the boson mass and the black hole spin. Those are 3 parameters. But now once you put this into a binary, you then need to know, okay, what is the mass ratio, number 1? What is the orbital angular momentum alignment with the spin angular momentum of the central black hole? What's the spin of the small black hole? And all of these things then combine to result in basically a plethora of different dynamics and different impacts of the cloud on the in-spiraling black hole, but also on the presence of the cloud, okay? So basically there are a bunch of effects that happen that people are trying to understand at the moment. So these things, for instance, there are resonances. So basically these are particular ways for this perturber to basically pump a bunch of energy from the superradiant state that has built up into a decaying state. And this decaying state will then basically accrete onto the black hole. And therefore, as the binary goes through this resonance, a bunch of energy from the superradiant state is then falling back into the black hole and basically destroying the cloud in the process. But then there are also things like, for instance, what people tend to call ionization. So basically, ionization is where this perturber is now able to perturb the cloud to such a degree that it emits scalar waves and therefore loses energy through that channel. And then there's a bunch more effects here that people are still working on, okay? So there's basically a whole machinery to trying to understand these effects at the moment, basically in preparation for Lisa. Okay. Are there any remaining questions? Yes, yes. So, right. Yes, in many different ways. So, so by environment, you might mean, an accretion disk, for instance, or you might mean a secondary black hole that spirals into the first black hole. And depending exactly on what the environment is, it then depends. So for instance, if you have an axion-photon coupling or a kinetic mixing, and you have an accretion disk, the accretion disk is the natural source of photons, okay? So you might expect that there's a very strong interaction between the axion and the superdense cloud and the accretion disk that contains a bunch of photons. Or conversely, you have a dark photon field that grew to form a superdense cloud, and that might interact with these photons on the accretion disk. And in both cases, the axion and the kinetic mixing, people are still trying to understand exactly how, but the impact can be very drastic. So that would be in the case of the accretion disk. Then, of course, in the case of the binary, the cloud could be completely destroyed. It will, have some effect on the binary. So, for instance, the binary might develop a lot of eccentricity, these kinds of things. So, yeah, it has a huge effect. That's right. Yeah. So, kind of the assumption is that once the black hole was formed, even quantum fluctuations of this bosonic field can trigger the instability. I would suspect it is negligible, yeah, because you have up to 10% of the mass of the black hole is contained in the cloud. And so the cloud can be very spread out. And so this mass is already just a fraction of the black hole's mass, but it's also spread out over a much bigger volume, okay? But then, of course, 10 is kind of the maximum possible. A more realistic number is some fraction of the 10. And so then you have the fraction of the mass of the black hole is contained in a very big volume. So I just suspect it's negligible, but I've never thought about it, so I'm not sure people have. Right, so I think the overall amplitude might still be negligible. The time dependence might be tricky actually, because then it depends on the light crossing time of the gravitational waves from the start to the end of the cloud. And then the question is, okay, how does this time compare to the oscillation time? And so maybe you kind of get an averaged version of the lensing. And so the time dependence of the cloud might not matter at all. But yeah, I don't know. Yeah, I suspect then it would have some impact that you might see. Yeah. Although it might be very difficult to look for it then.
So are there any other questions? Okay, so if not, let's thank our speaker.